Well, welcome back everyone, and again, thanks for coming. What I'd like to do now is talk about the last of the general explanations, the general reasons for finding an association in any type of study. And again, I'm going to be using the cross-sectional study design that we've been talking about up to now to explain this last alternative explanation. It has to do with statistical chance. Now that's what Marcello has been talking about recently in his lectures. And the way we designed this course is we delayed presenting a lot of the epidemiology material until Marcello had sufficient time to lay the foundation, the statistical foundation, for us epidemiologists to use that information. So now that he's covered that information, I want to talk about how we epidemiologists try to factor in the role of chance as the reason for finding an association between one factor and another in an epidemiologic study. So for the last time, this is the data we've been dealing with, the cross-sectional study from the Framingham heart study data set, looking at the relationship between smoking and heart disease at the 1956 examination. And again, what we found out is we observed a prevalence ratio of 0.82, saying that the prevalence of heart disease among the smokers, about 4%, was less than that among the non-smokers, which was about 5%. The prevalence among the smokers was about 80% of that of the non-smokers. That's a measure of association. And one reason for that measure of association could just be chance alone. And what I mean by that is the following. What we have in this study are 2,181 smokers and 2,253 non-smokers. Now, we might consider those 2,181 smokers as a sample of all the types of people who could have been in the Framingham heart study. And hopefully we can consider those 2,181 smokers in our Framingham heart study as a representative sample of the larger population of potential smokers that we could have enrolled in our study. Well, that's what Marcello's been talking about in his lectures, the idea of samples drawn from populations and how random samples will give us estimates of quantities that exist in some larger general population from which that sample was taken. So what we had in this case is we might consider our 2,181 smokers as a representative sample of all potential smokers that we could have enrolled in our study. So when we look at the observed prevalence among our smokers and see a prevalence of 0.0394, about 4%, that's an estimate of the true probability of having coronary heart disease, the true prevalence of heart disease among all smokers who could have been potentially selected from our study. And as an estimate, it could be a little bit above the true value, it could be a little bit below the true value, just based on what we call chance alone. Sampling variability means hopefully our random samples characteristics reflect those of a larger population. But remember, it's only based on a small percentage of that larger population. And therefore, the characteristics we observe in our sample, a prevalence of 0.0394, is only an estimate of the corresponding prevalence in this larger population of all potential smokers. And our observed prevalence might be a little bit lower or a little bit larger than that true prevalence that we would have seen if we enrolled all these potential smokers in our study. Therefore, our observed prevalence might be less than or it might be greater than that true prevalence just by chance alone. And the same thing can be said about the non-smokers and their observed prevalence as an estimate of the prevalence of heart disease among potentially all non-smokers we could enroll in our study. So how do we epidemiologists quantify the role of chance? Take into account that the numbers we see in our study are only estimates of numbers that would exist if we enrolled everybody we could, all potential people, in our study. Well, we do that statistically using two of the techniques that Marcello's been teaching you about statistical inference. We use tests of significance, and we develop, and from tests of significance we report p-values, or alternatively we develop confidence intervals, calculate confidence intervals, and I'd like to talk about each of those individually. A test of significance is a measure of how consistent the data we have. The data is that 2x2 table we've been looking at with the prevalence ratio of 0.82. How consistent is that with a statement known as the null hypothesis? The null hypothesis says that the prevalence of heart disease in general among smokers is the same as the prevalence of heart disease in general among non-smokers. Meaning, in general, there's no true relationship, no association between smoking status and the existence or non-existence of coronary heart disease. In general, the true value for the prevalence ratio would be 1.0. That's what the null hypothesis states. A test of significance is just asking the question, how consistent is our data, which reports a prevalence ratio of 0.82, with this statement that says the true value for the prevalence ratio if I enrolled all smokers and all non-smokers would be a prevalence ratio of 1.0. How consistent is our data with that null hypothesis? That's what a test of significance is trying to do for you. Marcello is teaching you about various tests of significance, chi-squared test, t-test, various tests that statisticians use to measure associations. I'll leave that to his lectures to describe where it comes from. But what we develop from a test of significance is a p-value, a number that reflects how consistent our data is with the null hypothesis. It turns out that if the p-value is large, then there is support for the null hypothesis. We say our data is reasonable to expect when the null hypothesis is true. On the other hand, if the p-value is small, we take that to mean there's little support for the null hypothesis. The results we see in our data set are not typical for what we expect to see when the null hypothesis is true. So that's what a test of significance is trying to do. It's trying to tell us whether that prevalence ratio 0.82 that we observed in our data set, based on the smokers having a prevalence of 4% and the non-smokers having a prevalence of 5%, prevalence ratio around 0.8, whether that is just a chance finding when the true null hypothesis is of no association. I'll show you the result of that test of significance in a minute. The other way we epidemiologists take into account the role of chance is by building confidence intervals. Our data says our best guess, based on our data of the prevalence ratio, the association between smoking and heart disease, is a prevalence ratio of 0.82. We realize that that 0.82 prevalence ratio is based on estimates of prevalences of heart disease among smokers in general and estimates for the prevalence of heart disease among non-smokers in general. Therefore, our prevalence ratio 0.82 is just an estimate of the true prevalence ratio that we observe if I enrolled all the smokers and all the non-smokers that I could potentially get into my study. Well, a confidence interval is going to give me a range of values. It's going to be built around my best guess, 0.82, but it's going to go above and beyond that. It's going to give me a range of values as believable results or believable estimates for the true prevalence ratio based on what I have in my data set. So it builds, instead of reporting a single estimate, 0.82, it gives a range of estimates, all of which are reasonable estimates based on what I observe in this data set. So here's my data. Again, remember, I saw a prevalence ratio of 0.82. The 95% confidence interval, what Marcello will be teaching you, built around that prevalence ratio, says my guesses for the true prevalence ratios, as reflected by a 95% confidence interval, can be as low as 0.62, suggesting that smokers have only a 60% prevalence of non-smokers, or as high as 1.08, saying prevalence of heart disease among smokers is 1.8 times that of non-smokers. So that's one way we can quantify the role of chances by presenting a confidence interval. The other thing we could do is we can report a p-value from a test of significance on this data set, and again I'll let Marcello describe how these tests of significance are performed. I get a p-value of 0.17. Remember, I said large p-values support the null hypothesis, small p-values do not support the null hypothesis. Well, what's a large p-value? What's a small p-value? In usual practice, 0.05 is usually the cutoff that people use to declare something statistically significant, in some sense to separate large from small. 0.17 is bigger than 0.05. You could say these results are not statistically significant at the 0.05 level, and therefore there is support for the null hypothesis that the true prevalence ratio is equal to 1.0. Now, before I leave this example, let me just point out the similarities between the conclusions you reach from the test of significance and the conclusions you reach from the confidence interval about the role of chance. The p-value, 0.17, that we observe in this data says the data supports the null hypothesis as a reasonable value, a reasonable estimate for the true prevalence ratio. If I look at the confidence interval, notice that it contains the number 1.0. It's in that range of values. So it is one of the numbers that is supported by the data based on the values of that confidence interval. So by either looking at the confidence interval or looking at the p-value, we reach the conclusion that these data, even though we see an association of 0.82, do support the null hypothesis that says in reality there really is no true association. So p-values, confidence intervals are often reported as parts of epidemiologic research to show the role of chance, to quantify the role of chance as being the likely reason for finding an association between two factors in your study. Well, that's all I wanted to say now about chance. When we come back, I want to tell you about some sources of data that you can use to develop cross-sectional studies. So I'll see you next time.